CC plus Q1 minus Q2 is everything equal to 0. But S, which is again the force that your fluid gives to your structure, is equal to minus pi 0. So if I take pi 0 on the other side, I find exactly S, which is the equation, the vector equation that we have written right there. Alright, so right now we have a vector equation, but in this case our force is acting only on the x-axis. So basically G does not make any contribute, and pi 0 along axis, so the component of pi 0 along the x-axis is equal to 0. So if this is equal to 0, it means that the component of Sx is again equal to 0. So let's project the vector equation on your x-axis, and we find that 0, so Sx, is equal to J, no contribute. Pi 1 is positive in the vector equation, so it's exactly the physical definition of pi 1. It's along the x-axis, so it's plus. So it's plus pi 1 component. Then we have pi 2, but pi 2 is direct against the section number 2. It means that pi 2 is physically good in this scheme, but it's on the other side, it's plus in the vector system, but it's in the other side respect of x, so it's minus pi 2. Then we have pi cc, which is direct in this way. We don't see right there because it's a distributed force pressure in this part of your system, so it will be plus pi cc. Then we have Q1. Q1 is the flow which is entering inside your section number 1. So physically it enters in the section. It's good, well, right here, so it's positive in our vector system, vector equation, sorry. So it's plus Q1. Then we have Q2, but look that Q2 is something that is going outside from your control volume. So basically it goes outside. It means that if I want to be correct with my equation, vector equation, I can just write this Q2 like a vector in the other verse with minus Q2. So saying Q2 from left to right, or saying Q2 minus Q2 from right to left, is exactly the same thing, which means that right here minus Q2 is concord with our system, with our vector equation, but it's on the other side of x, so it becomes minus Q2. Alright, let's try to define who is who. So we have pi 1, which is the barycentric pressure P1 times the area of cross-section number 1. Then we have pi 2, which is exactly the same, so it would be pi 2 times A2. Then we have pi cc, pi cc is the pressure related, because it's really close to section number 1, so it's pressure number 1 that is multiplied for the difference of the two areas, so it would be A2 minus A1. Then we had, and these are all the pressure forces. Then we had the continuity, the motion equation, which is Q1, and it's equal to the density of the fluid times the volumetric discharge of the fluid times the velocity of the fluid, of the flow. So it will be V1 in Q1, because remember that the volumetric discharge is equal from section number 1 to section number 2, while it's not the same for the velocity. So in section number 1 I will have velocity number 1. Then the same for Q2. Q2 is equal to rho times the volumetric discharge times the velocity in section number 2. Alright, so let's go on with our passages. And we can get that, recalling our equation, which was P1 minus P2 plus pi cc plus Q1 minus Q2 equal to 0. We substitute all the things that we have written right before, and we can say that pi1 was P1 A1 minus P2 A2 plus P1 A2, sorry, P1 times A2 minus A1 plus rho Q V1 minus rho Q V2 equal to 0. Okay, then P1 A1 goes away, so by and by we get that A2 multiplies P1 minus P2 plus we have rho Q that multiplies V1 minus V2, which is equal to 0. Then we separate these two things and we get that A2 times P1 minus P2 is equal to rho Q times V2 minus V1, because if I bring this stuff on the other side becomes minus rho Q V1 minus V2, I put the minus inside the branches and it becomes V2 minus V1. Remember that Q is equal to V1 A1 and it's equal to V2 A2, so I can write A2 P1 minus P2 equal to rho. Instead of Q, I can say, for example, V2 A2 that multiply V2 minus V1, so A2 goes away, and finally I find P1 minus P2 as rho V2 that multiplies V2 minus V1. Observe that since V2 minus V1, remember that in our scheme, this is clear, this was A2, this was A1, so V2 is lower than V1, which means that V2 minus V1 is lower than 0. Okay, but if this is lower than 0, it means that also P1 minus P2 is lower than 0, hence P2 is greater than P1. That is what we have seen before in the scheme. Last step is that, for example, we want to get this thing for pi1 minus pi2 and insert it in right here, when we have applied Bernoulli's theorem and we have compute delta H. So it was that delta H is equal to P1 minus P2, which is right now rho V2 that multiplies V2 minus V1, alright, over gamma plus V1 to the power of 2 minus V2 to the power of 2 over 2g. Gamma again is rho times g, so rho goes away, and you get that is V2 to the power of 2 minus V1 V2 over g plus V1 to the power of 2 minus V2 to the power of 2 over 2g. So it's 2g on the denominator that multiplies 2 V2 to the power of 2 minus V1 V2, sorry, 2 V1 V2 plus V1 to the power of 2 minus V2 to the power of 2. Hence, this is 2V2 to the power of 2 minus V2 to the power of 2 gives you V2 to the power of 2 minus 2 V1 V2 plus V1 to the power of 2 over 2g, which again is V1 minus V2 to the power of 2 over 2g. Hence, finally, we have expressed the total head between the difference of the total head before and after the sudden enlargement, only knowing what? The difference of the velocity between the two sections. It is also possible to demonstrate that this is related to the difference of the cross-section, because, for example, take another paper, so the trees will be very happy. For example, if I want to express everything in terms of cross-section, we have, remember again, that Q is equal to V1 A1, which is equal to V2 A2. Hence, if I, for example, write V1 in terms of V2, I obtain that V1 is equal to A2 over A1 times V2. And substituting with the previous result, we obtain that delta H is equal to 1 over 2g that multiplies, it was v1 minus v2 to the power of 2, which becomes 1, which is a2 over a1 v2 minus v2 to the power of 2. So this v2 is common, I can put it outside to the power of 2, of course. It becomes v2 to the power of 2 over 2g that multiplies a2 over a1 minus 1, everything to the power of 2. But observe that this stuff right here is your k. So finally we have the formulas for the sudden enlargement, which means that when you have the sudden enlargement, you can just consider the ratio among the cross-section of your area. Minus 1 to the power of 2 multiplies by the following velocity in the part where you have the higher cross-section. In the next lessons we will see how to compute the other concentrated energy losses. Hence, again, there are some exercises uploaded on the website, but again, if you want to solve any doubts or you have any questions about this stuff that we have seen right now, don't hesitate to ask me.